Welcome to Season 4 of Stan's Revenge. A new exciting chapter awaits. My name is Noah Almond. I've been experimenting with Stanley Meyer's water fuel cell technology for over 14 years. In previous seasons, I've made exciting discoveries in his technology, namely the operation of the electrical polarization process. This is unlike traditional DC electrolysis where low voltage and high amperage is utilized. As always, no electrolyte or additives are used in my cells. Only ordinary, natural water is utilized. In this season, I pushed the boundaries of my water fuel cell technology further in my latest attempt to break the glass ceiling of 150 volts. Join me as we unlock the secrets. This is Stan's Revenge. Alright, hello everyone. I am Noah Almond, aka Stan's Revenge. This is the electrical polarization process, part 2. Apparatus, circuitry, controls, and operation. Let's get started. Layout. The complete water fuel cell circuit can be categorized into the following. 1. Power supplies. 30 volt primary and 12 volt controls. 2. PWM signal generator. Square wave signal generation. 3. Driver snubber. Circuit and feedback loop for transformer primary coil. 4. Transformer/VIC. Responsible for power amplification and waveform balancing. 5. Cells. Stainless steel tubes. 30 volt variable PSU. The 30 volt power supply unit delivers power exclusively to the MOSFET and primary coil. It is the primary power source for the VIC circuit and EPP. The positive terminal of this PSU is connected directly to the primary coil of the VIC transformer, separated only by a diode, with current respective. The negative terminal of this PSU is bonded to the 0 volt earth-ground connection of the power supply unit. This bonded negative terminal connects to the S terminal on the MOSFET, separated only by a diode, with current respective. Snubber. The snubber is a simple series resistor, capacitor, and diode which is connected in parallel with the transformer's primary coil. The snubber's function is to reduce transients, noise, and spikebacks on the 30 volt positive rail. This effectively eliminates damage to the MOSFETs and other driver components. The 30 volt PSU positive terminal also connects to the snubber by way of reverse polarity 50 volt 20 amp Schottky rectifier diode, connected to a 474 nanofarad 63 volt polycarbonate capacitor, connected to a 10 ohm 100 watt wire wound resistor. This snubber resistor then connects to the D terminal on the MOSFET, shared with a connection to the VIC primary coil's negative terminal. Please note that these are likely not optimal snubber values, but they do prevent MOSFET damage fairly effectively. You may need to modify these values to obtain optimal operation. 12 volt PSU. The 12 volt PSU delivers power exclusively to the PWM signal generator. The PWM signal generator consumes minimal amperage, less than 30 milliamps, and the 12 volt PSU is not connected to any other part of the VIC. PWM. The PWM delivers a continuous square wave signal directly to the MOSFET. The PWM consumes a negligible amount of energy, less than 30 milliamps, as the MOSFET is responsible for delivering up to 30 volts 10 amps from the variable 30 volt DC PSU. The PWM has a VIN plus and a VIN negative that connects directly to the 12 volt PSU. The PWM also has a PWM out which connects directly to the G terminal on the MOSFET. MOSFET. The MOSFET in my apparatus is mounted to an aluminum computer processor heatsink. This is accomplished by drilling a small hole to accommodate a screw or bolt that can secure the MOSFET to the heatsink. A thin layer of thermal paste is utilized for efficient heat transfer. The MOSFET cooling fan, or CPU cooler, is connected to the 12 volt PSU and consumes minimal amperage. As previously mentioned, the MOSFET terminal connections are as follows. G. Output of signal generator, or PWM. D. Snubber, a negative terminal of the VIC primary coil. S. Negative terminal of the 30 volt PSU. Transformer/VIC. The specific transformer I utilize has 8 total leads. The standard step-down transformer is connected in reverse, rather inversed, to create a step-up transformer. This means we use the secondary coils as the primary and the primary coils as the secondary. Each respective coil has 4 leads and each should be connected in a bifilar mode, which is considered center tap, open ground, so that the primary coil is bifilar mode and the secondary coil is also bifilar mode. HV diode location and orientation. This is very important to note. This is in relation to the VIC diode contained within Stanley Meyer's VIC schematics. The specific diode location and polarity orientation can be modified for different operational modes and generated waveforms. In my specific application, the colored wires are connected as follows. Yellow, black. This is the primary coil positive and negative input from the PSU or MOSFET. Orange to red. Primary bifilar center tap. These are connected together. Blue. This goes to the VIC diode with polarity respective. Purple to gray. This is the secondary bifilar center tap. These are connected together. Brown. This goes to the cell's negative terminal plus a cell diode if applicable. VIC diode. This goes to inductor A, or the balancing inductor. Balancing inductor. This goes to the cell's positive terminal, plus a cell diode if applicable. Multiple modes of operation are possible. If waveforms observed at the cell terminals are not appropriate, EOP, experiment with different VIC diode locations, like on the secondary's positive versus negative terminal. Diode polarity orientation, so flipping it reverse positive or negative. And balancing inductors polarity orientation, reversing positive and negative. Balanced inductors. The transformer in my apparatus is wound with an additional coil, herein called the balancing inductor. The function is to match the inductance of one of the secondary coils. This inductance of this balancing inductor should match a single secondary coil. The inductance to match would effectively be measured from the secondary's negative terminal to the secondary's bifilar center tap. The secondary's bifilar center tap is essentially the electrical ground, also known as 61 or J, as seen in Stanley's VIC schematics. Again, the custom wound balancing inductor wrapped on top of entire toroidal transformer should measure the same inductance of the reference single secondary coil. This balancing inductor is connected in series to the secondary's positive terminal just after the VIC diode. The VIC diode acts as a wall. Inductance values in front of this diode are null. Therefore, the balancing inductor must be on the terminal that hosts the VIC diode, so that the opposite coil's inductance is matched to the balancing inductor, essentially inductor A, inductor B on Stanley's schematics. When operating the apparatus, by observing the oscilloscope channel 3 and channel 4, you can make empirical observations about which terminal has more inductance. Then you can remove individual winds accordingly to achieve a balanced EOP at the cells. In the WFC operations section, you will understand how to perfectly balance the inductance within the VIC. Inductor individual windings will likely need to be removed to perfectly balance the waveform. Series cells. In my apparatus, a single cell, as referenced, generally contains 6 individual cells, which is also 12 concentric positive-negative tubes respectively. This cell verbiage typically represents a 6x1 cell. As part of my apparatus, additional cells can be serially connected. In my application, up to 6x6 cells or 32 individual cells have been tested. Additional cells over 32 may provide diminishing performance. Cell terminals are defined as the first positive terminal input and the last series negative terminal output, first in, last out. Oscilloscope. In my present apparatus, there are 4 points of observation for the oscilloscope waveforms. The channels are as follows. Channel 1, yellow. This is the PWM signal generator's output being delivered to the MOSFET. This shows the physical square wave signal that is being delivered to the input of the MOSFET. Channel 2, red. This is the variable 30-volt DC positive rail. This is simply for monitoring the DC rail for spikebacks, transients, and other harmful noise from the VIC's operation. It's good for snubber tweaking. Channel 3, blue. This is the positive terminal of the series cells, first in. This is for monitoring the cell's positive pulse to effectively realize and utilize EOP. Channel 4, green. This is the negative terminal of the series cells, last out. This is for monitoring the cell's negative pulse and to effectively realize and utilize EOP. Note that all oscilloscope channels do not have a probe reference ground. Floating ground is utilized for all readings. Channel 3 and Channel 4 probes are set to 10x reduction. Channel 3 and Channel 4 are centered on the oscilloscope display so that EOP can be effectively displayed and realized. Voltmeter. The voltmeter is connected to the cell's positive and negative terminals in the same location as the oscilloscope's Channel 3 and Channel 4 respectively, first in, last out. This provides a value of the difference in voltage potential across the entire span of cells, or capacitors. Amp meter. The amp meter is connected in series to the cell's positive terminal only, first in. This provides a value of amperage being consumed at the cells. Normal operating ranges in my apparatus are from 200 milliamps to 1 amp, with some specific modes or extreme operation consuming up to 2 amps. Cell diodes. High voltage, fast recovery diodes have been observed as aiding EOP in certain circuit configurations. Typically speaking, when these diodes are placed at the cell's positive and negative terminals, first in, last out, with current respective, reverse polarity spikes are reduced during the pulse off time. This can help produce better looking EOP waveforms and retain more polarity difference in the cells during off time. Water fuel cell operation. Control overview. The overall goal of water fuel cell operation is to obviously get the highest gas production possible. To achieve this, voltage potential must be maximized by tuning in to the LC circuit's resonant frequency. Finding this frequency is fairly easy. Start the PWM with 50% duty cycle and a frequency of about 500 Hz. Make sure your primary variable PSU is set to 0 volts every time you power on. Begin by powering on the apparatus and increasing the primary PSU voltage to approximately 12 to 15 volts. You may notice a small amount of gas production at the cells. If you do, you're off to a great start. Observe your oscilloscope, paying close attention to Channel 3 and Channel 4. Look for increasing polarity differences and opposing pulses. At low voltage or out of resonant frequency, the waveform may not be true EOP yet. True EOP is sometimes not fully realized until you achieve higher voltage levels at the cell. If you are not getting defined polarity differences of 3 volts per tube or more, check your VIC connections, as you may need to modify it by connecting it in different polarity mode or configuration. With my apparatus, you should be able to achieve voltages up to 5 volts per tube. If you see some gas production and opposite polarity pulses on the oscilloscope, and the voltmeter reads appropriate corresponding voltage across the cells, try increasing the frequency to determine if the cell voltage rises. If the cell voltage diminishes, decrease the frequency until a maximum voltage is reached. Once you find this resonant frequency, you can then increase the voltage on the variable DC PSU to achieve a moderate gas yield. In addition, you may increase the PWM's pulse duty cycle up to 85% for maximum gas production. Be aware that this will consume many more input amps, typically up to 6 or 7 amps. Increasing the duty cycle will also increase the current flow in your cells. Adjusting frequency or duty cycle while operating at high or maximum input voltage may damage your driver. It is recommended that all tuning be done at moderate voltage levels. Under present operating conditions, amperage at the cell is typically at about 1 amp and can even be as high as 2 amps in specific extreme operating conditions. Remember, the key is to keep amperage minimized and voltage maximized. Your specific VIC may operate with different parameters than my apparatus, so be curious and determine your own optimal conditions. Before modifying any part of your VIC or touching any connection, verify that all power is turned off and that the cells have been grounded or shorted. Stored energy in the cells, or water capacitors, can be discharged throughout any part of the circuit. Be careful. For safety, I incorporate a set of relays that automatically short the VIC in cells to discharge all energy when the power is turned off. These safety relays can be referenced in my HVIC matrix switchboard videos on YouTube. You should then realize and observe maximum voltage potential on your oscilloscope. Upon initial operation, your observed channel 3 and channel 4 waveforms will not be equally opposite. To fine-tune your VIC circuit, observe the blue waveform in relation to the green waveform, channel 3 versus 4. Observe and make note of how many vertical grid blocks, or volts, the blue waveform is achieving. For example, 4.0 grid blocks. Now observe and make note of how many vertical grid blocks the green waveform is achieving. For example, 3.5 grid blocks. Since both waveforms should be the same voltage, or take up the same number of vertical grid blocks, we clearly have a polarity imbalance. The key is to remove windings from the coil that is providing more blocks or voltage, or add windings to the opposite coil. Ideally, it's easiest to unwind some of your balancing inductor instead of adding more windings to your secondary's negative coil, inductor B. When you unwind or remove individual coils of wire, do so just a few winds at a time so that you don't remove too many. With some trial and error, you should be able to accomplish true EOP, maximize voltage potential, and minimize amperage at the cell. Water fuel cell management. You will notice after some use of the water fuel cell, the water will become dirty and discolored. Contaminants are pulled from the water during the EPP. Since only HHO and ambient air gases are leaving the cells, the water bath collects particulates and minerals released from the water. Once this water is saturated, the performance of the water fuel cell is likely to be affected. Utilizing larger water baths or chambers would reduce the rate of water saturation. Ultimately, the individual cell or group of cells would need to be shut down, drained, rinsed, and filled again with natural water. Values, calculations, and results. Here are the disclosed values for all the components of my apparatus. VIC diode, this is an FR207. The cell diodes are a UF4007. Snubber diode, Schottky rectifier diode, model 20SQ050. The type is used wherever a diode is necessary on the 30-volt DC driver rail. Capacitor, it's a 474 nanofarad, 63-volt polycarbonate capacitor. Numbers on the capacitor are 0.47 and K.63. Resistor, this is a 100-watt, 2-ohm wire-wound resistor. VIC transformer. These values are all measured at 1 kHz. Primary, single. Inductance 700 to 785 microhenries. Capacitance 32 microfarads. Resistance 12 ohms. The primary in a bifilar configuration 880 microhenries to 980 microhenries. Capacitance is 25.75 microfarads. Resistance is 26 ohms. Secondary's single coil is 330 millihenries up to 336 millihenries. Capacitance is 76.2 nanofarads to 77 nanofarads. Resistance is 459 ohms. The secondary bifilar mode inductance is 1.18 henries. Capacitance is 21.7 nanofarads. Resistance is 805 ohms. The balancing inductor. Inductance was measured at 250 millihenries up to 270 millihenries. Capacitance was 102.7 nanofarads. Resistance is 503 ohms. Water capacitors. The values of individual 6x1 cells can be seen in my previous YouTube videos. In my specific configuration, the span of 24 cells, 6x4, the inductance is measured at 151 henries. Capacitance is measured at 166 picofarads, and resistance is measured at 37 mega ohms. Calculations. PSU input power consumption. Typical amperage values under normal 29-volt test scenarios vary between 4 amps and 6 amps. For my demo video, a maximum value of 32 volts is utilized. The input amperage was 7.23. And the input watts was 231.72 watts. Cell power utilization. In my test video, SR120, we have the following values. The average input voltage was 32.06. Following by the next test, 31.99. And the final test, 32.06. The input average on the first test was 7.23, followed by the second test of 7.25, and the third and final test by 7.29 amps. Average input watts was 231.72, 231.92, and 233.71, respectively. The watts per liter is calculated at 758.18 watts, 735.18 watts for the second test, and 740.86 watts for the third and final test. HHO gas production test 1. Measurements at cell was 118.7 volts and 1.21 amps. The 0.5 milliliter bottle time to fill was 1 minute and 38 seconds. Multiplying that by 2, we'd get 3 minutes and 16 seconds to fill a complete liter of HHO gas. That equates to the decimal multiplier of 3.27. So we have amps times the minutes per liter gives us 4.6 amps per liter. Amperage times voltage times minutes per liter would be 546.02 watts per liter. Input watts, we were at 732.23 watts of input power. Footnote, you may look at these and be like, well, these are much over traditional DC electrolysis, and yes, they are. What I am showing here is the function of EOP, not really paying too much attention to the amount of energy that's being used. I am proving the function of the technology. Efficiency can be raised, but the function of the apparatus is what the purpose of these videos and my channel is about. HHO gas production test 2. Measurements at the cell, 118 volts, 1.12 amps. Time to fill bottle, 1 minute 35 seconds. That's 3 minutes and 10 seconds per liter. Decimal multiplier of 3.17, which brings us to 3.55 amps per liter, 418.9 watts per liter, and a total input wattage of 735.18 watts of power per liter. Test 3, measured 117.8 volts at the cell at 1.12 amps. Time to fill bottle, 1 minute and 35 seconds. Multiplier is 3 minutes and 10 seconds per liter of HHO. So the decimal multiplier, 3.17. So that equates to 3.55 amps per liter, which is 418.19 watts per liter, and 740.86 watts input power per liter. Conclusion. The EPP is a powerful, widely misunderstood phenomenon. As observed and recorded herein, my apparatus can produce nearly 1/3 of a liter per minute of HHO with just 1.12 amps consumed, when utilizing voltage potential as the means of molecular separation. Even though more than 400 watts is consumed input power, at the cells, the measured amperage is insufficient to create the amount of gas observed. The amperage is just a fraction of what present-day Faraday's DC electrolysis requires. This proves that voltage is performing the work, just as Stanley Meyer's patents, memos, and seminars profess. With just 1.1 amps measured at the cells, it is clear that the applied voltage potential of 118 volts, which is extrapolated to just 4.81 volts per individual pair of concentric tubes, delivered by means of the VIC as equal opposite polarity pulses, is the driving force in the physical process. Scaled to 3 times its present size, my apparatus would produce nearly 1 liter per minute, utilizing a total of only 3.5 amps. In this scenario, each apparatus would be identical, delivering 118 volts to each series of 24 cells at 1.12 amps. However, the total input power consumption would be approximately 740 watts. Final words. With further exploration, experimentation, and the application of Stanley Meyer's revolutionary technologies, a new future of clean energy and clean water can be realized. The fundamentals of the electrical polarization process are now understood and are applied to my apparatus and have been verified in my publications. With these fundamentals now proven and as even greater water fuel cell technology and efficiency is attained, this technology can be taken seriously by all to finally propel it to its destiny as one of the greatest technological discoveries of mankind. If these fascinating results can be accomplished with the limited resources, knowledge, expertise, and funding that I alone possess, there's no telling what this technology in the right hands would be capable of. Thank you again for watching this video. If you haven't subscribed already, please do subscribe. We got some great new things coming forward to you. Getting connected with a lot of great people. I want to thank each and every one of you for helping me out in this journey, giving me the support that I need to keep this moving. Again, my name's Noah Amen. I am Stan's Revenge.